field effect transistor, few kinds of MOSFET, the D MOSFET, E MOSFET, and so on. So in this chapter, frequency analysis, we will look at the response of the transistors, the BJT, and also the FET transistors. How come my slide is not on? This one is off. Okay, this is the one. Okay, let me put it on slideshow. Okay, as usual, I would like to, okay, Farastaki has started recording. Thank you, Farastaki. Okay, so the chapter is quite long, so let's recall back from circuit theory 1, where I have introduced you all a little bit on the frequency analysis. And when you mention about frequency analysis, what you should have in mind is the body plot and the phase plot. So let's recall back. For frequency analysis, it is actually in the x-axis. When you graph the frequency response, you will have in mind the x-axis will be the units of frequency, which is in hertz, and the y-axis is a unit of either it can be amplitude or it can be gain, and the unit can be actual value or nominal value or normalized value. So any amplifier have relatively constant gain over a certain range. For example, if you have a frequency response like in this figure, this shows a band pass filter. Recall, we have few kinds of filters. Talking about frequency response, in your mind, you must always associate whether the frequency response is in terms of low pass filter, high pass filter, or combination of both, which produce the band pass filter. Or if you do one after another, you can also have band stop pass filter. Okay, and the middle range of the frequency, the mid band, or you call it the bandwidth, depends on the arrangement of the circuits component. Okay, so a filter can also have the effect of amplification. So some amplifiers have relatively constant gain over a certain range, and sometimes it does not have any gain, or there is no response beyond the bandwidth of the working frequency. So this band of frequencies is called the bandwidth of the amplifier, and the mid-band gain is the values of an amplifier that is operated within the bandwidth. So the frequency response curve always have a certain range, and the bandwidth always start labeled as F lower cutoff, FC1, and F upper cutoff, FC2. Okay, and the mid band is the value at which the frequency response is maintained. Or from this figure, you will see there will be a drop at certain range, and the drop in terms of if your y-axis is in the scale of dB unit, it should drop at -3 dB. If and the maximum, if you have the y-axis, the gain of the amplifier or the gain of the circuit is normalized from 0 to 1 or 0 to 100, the maximum will be the flat frequency response. And the point here the 50% from, if the gain is 0 to 1, 0 to maximum, at 50% of the maximum response, that is the lower cutoff. And 50% at the higher cutoff, that is the range of the working frequency, the bandwidth. But in terms of dB unit, it should drop at negative 3 dB. If in the units of, it can also be 70.7%. So those three values depending on a different scale of the y-axis. Okay. The gain of an amplifier remains relatively constant across a band of frequencies. And simply, we have to find the working frequency. You simply, the working frequency is the bandwidth, is simply the lower cut, the difference between the upper cutoff frequency and the lower cutoff frequency. Okay, and these are the frequencies at which the gain decreased to approximately 50% of the mid-band gain. Okay, and an amplifier is operated at a DC cue point and is subjected to two types of signals, AC signals and DC signals. Often several amplifiers are cascaded by capacitors as shown below. So we can have amplifier of few stages. So between stage of the circuit, we will have coupling capacitor. For example, the first stage here, we have coupling capacitor CS. And the next to that, in between the first stage and the second stage, you have coupling capacitor CC in between. And at the output, we have another coupling capacitor. So the function of the coupling capacitor is to cut off the DC component. Okay? And with the presence of this coupling capacitor, it will influence the actual cut-off frequencies of the circuit. Okay, and we will have many, due to the many coupling capacitors, you will have few cut-off frequencies. So depending on the cut-off frequencies, the actual cut-off frequencies will be based on the type of the frequency response. If it is a low-pass filter, you have 3 coupling capacitors. The actual cut-off frequency will be the lowest cut-off frequency that influence the circuit. Later on, I show you how to calculate the actual cut-off frequencies based on the few coupling capacitor effect. Okay, now for a FET in bipolar and FET transistors, discrete amplifiers, emitters, and source bypass capacitors are often included so that emitter and source resistors can be used to stabilize the cue point without sacrificing the small signal gain. So this one is a BJT amplifier. We will have a coupling capacitor CE, which is connected to the RE. Okay, and the bypass capacitor here in this case are assumed to act as a short circuit at the signal frequency. So because you have this CE connected at the RE, parallel to the RE, so the current do not flow to the RE, so it bypass. So that's why it acts as the short circuit. So when we are dealing with frequency response, because frequency response is often described in terms of dB units, and dB is always a logarithmic function. So let's recall basics of logarithms equation. When we have a equals to b to the power of x in terms of logarithmic function, we can represent the function a equals to bx in terms of log function. X is actually log b of a. So for example, if we have a equals to bx and is equal to 10 or 100, and 100 is actually 10 to the power of 2. So therefore, x is actually log b or log of 10 of 100, which is equals to 2. So commonly, we can represent a simple logarithmic of 10. X is actually log 10 of a. So this is important. Recalling the logarithmic function is important for the calculation of decibel units. So increase in power level. Example, we have 4 watts to 16 watts. Does not mean that the audio level increased by a factor of 16 over 4, which is 4, but it is actually a factor of 2, because we have 4 to the power of 2 is 16. For a change of power from 4 watts to 64 watts, it is actually increased by a factor of 3, because 4 to the power of 3 is giving you 64. So in logarithmic form, the relationship of log 4 of 64 is equals to 3. Okay, and Bell, from the scientist named Alexander Graham Bell, who has defined the unit of Bell, can represent to the base of 10 G, gain of any circuit. The gain is equals to log 10 of a power output P2 over P1. And this is referred as Bell unit. But the Bell is will be very large. So the decibel is defined so that 10 decibel is actually 1 bell. So therefore, when we have gain function, G is equals to 10 log 10 of P2 over P1, it is simply unit of decibel. So thus we will have dB units. This is the foundation of dB for gain any amplifier. Example, we have G equals to 10 log 10 P2 over P1, and P2 is always V2 over R. V to the power V squared over R. Remember your equation of power. And because it is 10 log 10, and P2 can be in terms of V2 over R, so as P1, V2 over R of V1 and respectively. Therefore, you will cancel the Ri in the denominator and the numerator. So therefore, it will only give you V2 over V1. Both, we bring out the power to the outside. Therefore, and you can bring 2 in front of the function. Therefore, you will have 20 log 10 of V2 over V1. And the unit now becomes dB. So therefore, calculation of gain is always 20 log of the magnitude of V2 over V1. And V2 over V1 is simply the gain of a circuit. So from the gain equation in dB units, you no need to actually plug in the value of the resistance. So simply you take the ratio of the output voltage over the input voltage times 20 logarithmic of those ratio to produce a dB value of the gain. In terms of scale, dB scale, we will from 0 to about 160. This is range of power amplification. If you have a 0 value, there is no, you cannot hear the sound in terms of amplification of sound. But from the range of 0 to up to 120 dB, this would be the dynamic range. And a very loud rock band music has a dB output power of about 110 dB. But for average good working gain will be around 60 to 70 only. As long as 70, the performance of the circuit is good. Below than that, it's not that good. So this would be the optimum or optimum desired gain in dB unit. Now, the general frequency considerations. Frequency response, the frequency range in which an amplifier will operate with negligible effects from capacitors and devices, internal capacitance, are often called the mid-range. At frequencies below the mid-range, the coupling and bypass capacitors lower the gain, meaning that instead of having the maximum gain, it will have a reduced gain or zero gain at all. So only in the range of the mid-range frequency, the gain, the desired gain is obtained. Okay. At frequencies above the mid-range, stray capacitance associated with the other device can also lower the gain. So only at the mid-range, you have the optimum performance. Okay, so cascading amplifiers can limit the gain at high and low frequency. So if you have too many parts of the circuit, you cascade too many sections, it is not good also. So the cascading should be only for certain range only. Okay. Body plot of frequency response. For example, recall that the body plot is the illustration of the frequency response of an amplifier. The horizontal scale in this figure indicates the frequency and the vertical scale indicates the gain. Okay, so the gain here, you have, if the maximum unit, the flat response, here is the mid gain, AV mid. The mid band is always 0.707 or 70.7% of the mid gain, mid band gain, AV mid. Okay, and if you have a response like this, this is a band stop pass filter. But if you have this one, this would be the low pass frequency response. If you only have the opposite to the low pass filter, you have a high pass frequency response. The cutoff frequency here is any frequency at which the gain has dropped by 3 dB from its mid-range value. 3 dB is equivalent to 70.7%. Because at the flat response, it will be 0 dB. So if you change the scale of the y-axis in dB unit, you will have you go down is a negative value. The flat line is actually at the scale of 0 dB. So that's why the cutoff is always taken at negative 3 dB. Meaning negative means a drop lah. Okay. To find the half power, so we have F1 and F2 as the cutoff frequencies. The half power and the mid-band power output is the value of magnitude of power lah. Power is because we have AC input. If you have AC input, you only should take the magnitude of the V output. So PO is equals to VO squared over RO squared. Take this the magnitude, which is actually the value of the gain, mid-band gain, times the VI. Okay, so record AV is always VO over VI. So VO is AV times VI lah. Okay, so at half power frequencies, 1/2, which is 0.5, multiplied by this PO. And if you plug in the value, AV mid is actually 0.707, which is 1/3 times this value. And therefore, power, half power frequency, PO, HPF, is the value of 0.707 times the AV mid times the V input divided by the RO value. So for a normalized gain, normalized you can span or you can expand the range of the amplitude in the y-axis from 0 to 1. So the cutoff will be at 0.707, or if you multiply by 100, you will get 0 to 100, and the cutoff frequency will be at 70.7. So if you make a scale of 100, that will be the scale only. So normalization is actually a process of changing the scale. Okay, so now your gain AV over AV mid in dB unit is always equals to 20 log 10 of AV over AV mid. Okay. The mid-band value is equals to 1 maximum, or the flat response of 1, or equivalent to dB of 0 lah, or 100%. And therefore at half power frequencies is only 1/2, which is 0.707. So in other words, the bandwidth of the frequency response is from half power frequencies, which is from 0.707 to from the lower cutoff to the upper cutoff. Above than that, the gain, the circuit will not have an optimum gain. So it will change with frequency change. But over the working frequency, within the bandwidth of the circuit, the performance is same, flat, same response, despite of changing frequencies of the input and output of the signal. I suppose in lab 1, you have, or is it in this, I think this semester, you will have lab year 2 lab year 1 was last semester, right? So in this semester, you're going to do one lab for frequency analysis, where in order for you to evaluate the frequency response, you will evaluate changing the frequency, what is the effect on the output. So in this range, from 100 to 100,000, 100,000 is 100 kilowatts. You will have, if you input, for example, if you have gain of 1, you input voltage of 2 millivolt, for example, you will get output of 2 millivolt also. Or maybe you can input 5 volts. The output will be also 5 volts. But if your frequency is lower than 100, say for example, you make a frequency of 30 hertz. 30 hertz somewhere here. You input voltage of 5 volts, output maybe only 1 volt. So the output is very small compared to the input, because it is lower than the cut-off frequency, because you're using 30 hertz signal. If you use 100k hertz frequency of the V1, you will still have output of 5 volts. Input 5 volts, output also 5 volts. But if you increase the frequency to, for example, 1 megahertz, you input 5 volts, you would get the output of less than 5 volts, because the midband will be a gain of 1. Whatever input you introduce, you will produce the same output in terms of amplitude level. Okay. All right. In terms of decibel, just now it was normalized gain. Now, decibel plots. For decibel plot, the midband is always at the level of 0 dB. And the 0.707 is equivalent to negative 3 dB. And this midband frequency is actually 20 log 10 of 1, which is giving you a value of 0. So the flat response of 0 dB. And the cut-off frequency thus is 20 log of 10 of 0.707 tadi lah, 1 over 2 is actually 0.707. And 20 log of it is equals to negative 3 dB. Okay, for phase plots, the phase response will be flat over the range of the bandwidth. So for the example shown here, it should be flat from 100 hertz to about 100. I think this one is 500 kilohertz. So above than that, and flat at 180 degrees phase angle. So 180 degrees is simply input is positive, output will be negative, because we are dealing with AC signal. Frequency response always have AC signal. The DC signal is a static signal. So that's why when talking about frequency response, you also need to consider the phase response, not just the magnitude response, but also the phase response. Okay. Now we need to evaluate the effect of the frequency response for the low frequency and high frequency response also. So for low frequency analysis, let's consider simple passive filter. So if you have a circuit of section having a capacitor and a resistor, and you measure the output at VO across the resistor, you will produce a low pass filter actually, if you recall. And here your capacitor is at the input, and imagine you supply the voltage at a very low frequency. For example, 1 hertz. 1 hertz is 1 cycle, 1 second, 1 cycle. If it is very small than that, it is like not changing at all. So when very low frequency, this section will appear as if it is an open circuit. So if DC signal at frequency equals to 0 hertz, that would be DC, a continuous signal. XC, the reactance, is equals to 1 over 2 pi f. You will have a impedance of infinity, or very high impedance, very high resistance. Okay, but when you increase the frequency, say for example, you introduce in 1 second thousands or millions of cycles of signals, you will see the reactance is equals to 1 over 2 pi fc, and f is very large number. 1 over very large number, you will produce 0.0000, almost a zero value. So the reactance xc will then becomes almost to the value of 0, and 0 is different from infinity value. Okay, and therefore you will have at very high frequency it's almost 0, but at low frequency you have infinity response. Infinity means very large response. So you would say you have a response at low frequency, but above the cutoff frequency, 0 response. So in other words, this is the response of a low pass filter. So here VO is equal to 0, but for the high frequency response, VO is going to be VI. Wherever you supply at VI will be the value of VO, because the section of the capacitor is simply observed as if it is a short circuit. Whereas for low frequency, the section of having the capacitor is an open circuit. So that's why you have 0 output here. Whereas in the high frequency response, you have a output equivalent to the value of the input. Okay. Now you have not the low pass filter, but this is the high pass filter response. When the frequency increase, the capacitive reactance decreases, and the output voltage increase, and the gain also increase. And the gain will be VO over VI, and the gain will be normalized gain will be 1 gain, because you have whatever you give the input, you will see at the output. Okay. High pass, I think this one is high pass. Okay. let's consider voltage divider rule. You will have VO is equals to R times VI divided with the R plus the reactance due to this capacitor. Okay, and the magnitude of VO is equals to RV divided with magnitude of R squared plus X, reactance of the capacitor squared. When the XC is equals to R, because XC is changing with respect to the changing of frequency. Sometimes if your capacitor is, if your input signal is low frequency, the reactance will be different. If the frequency is high, the reactance of the capacitor is also different. And then, therefore, you will produce the frequency depends very much on the reactance of the capacitor, which gives the value of the impedance or the resistance of the capacitor. And we know that the reactance is always 1 over 2 pi Fc. Therefore, if you manipulate the equation, you can have equation for the frequency. It is simply 1 over 2 pi times Rc. Okay, and the value of the output VO is equivalent to 1 over 2 of V1. Vi or V1 is the input of the circuit. Okay, in terms of logarithmic, logarithmic is dB units. Gain, the gain of voltage gain GV is equals to 20 log 10 AV, which is equals to 20 log 10 of 1 over sec 2, and it is equivalent to negative 3 dB. Okay, when AV is VO over VI equals to 1, which is the maximum value, GV will be equals to 20 log of 10 of 1, which is 20 times 0, and the value is 0 dB, the flat response or the mid band. Okay, the gain now is equals to VO over V1, VO over VI is equals to R over R minus the JX. This R minus JX is the impedance of the due to the capacitance present. And if you evaluate this one, you will get AV is actually 1 over 1 minus JF1 over F. And this will give you the magnitude and phase. The magnitude gain will be VO over V1. And the phase will be tangent inverse of F1 over F. When F is equal to F1, F equals to F1, the magnitude of the gain is going to be 1 over sec 1 plus 1 squared, which gives you a negative 3 dB. So in logarithmic, the gain in dB is equals to negative 20 log 10 F1 over F. So instead of using the value of voltage input, you can also evaluate the gain in terms of the frequency. Okay, so at F equals to F1, F1 over F is equal to 1. Therefore, you will have negative 20, you will have 20 log 10 of 1 is equal to 0. But if you have frequency F is half of F1, so you will have the ratio of F1 over F down becomes 2. So negative 20 log 10 of 2, you will have a negative 6 dB. If you have the F equals to a quarter of F1. Now F1 over F is equals to 4. Therefore, your negative 20 log 10 of 4 will be negative 12 dB. And if you have F is 1/10 of F1, your ratio of F1 over F is equal to 10. And therefore, your dB unit, 20 log 10 of 10, is become negative 20 dB. So these are, without knowing or without using the actual value of the voltage input, simply by evaluating at different frequencies, you can also calculate for the gain of the circuit. So here you know at half frequencies you have negative 6 dB. At same frequency you have 0 dB. Half frequency gives you negative 6 dB. A quarter of frequency gives you 12 dB, negative 12 dB, but 1/10 will give you 20 dB, and so on. And in terms of the frequency response, we can plot a quarter, half, F equal to same input F, twice, 3 times, 5 times, and so on. And the value will be at 1/4, 1/10 will be at negative 20 dB. Same frequency F1 and F2 the same, should be at negative 6. Negative 3. Negative 6 will be half. F1 is half of F. Okay, and in that way, we can, instead of using logarithmic to the base of 10, we can also use logarithmic to the base of 2, or we call it octave. So 6 dB is actually, you can represent 6 dB per octave, which is equivalent to 20 dB per decade. Decade means your base logarithmic function is 10, whereas octave base is base of 2. And okay, now if you consider a BJT amplifier, low frequency response, at low frequencies, the reactance of the coupling capacitors CS, CC, and the bypass capacitor CE affect the circuit impedance. So here you have voltage divider arrangement for this BJT. So for voltage divider circuit, voltage divider bias always have R1, R2 here, and you have RC. CS is the coupling capacitor for the input side. CC is the coupling capacitor for the output side, and CE is the bypass capacitor. So there will be different function for the capacitors present here. The two capacitors CS and CC is simply for the coupling capacitance, whereas CE is the bypass capacitor, so that current do not flow to the RE. It only bypass to this CE. So for this one, this circuit, you can convert into a hybrid equivalent circuit, small circuit equivalent or hybrid parameters, and we will have this part is actually this part, so that R1, R2 is actually in the input side, RC and RL. RL which is connected across the coupling capacitor C2 or CS here in this case. Oh, sorry, CC. We have CC here. And you will have RC parallel to RL. And this internal side, this BJT has RO value, and the PN junction here will have beta IB value. And at the input side, you will have beta RE. And you will have the point B is actually connected to the point C. Okay, so the parallel R1, R2 can be represented as R prime. Okay, so now let's see the effect of coupling capacitor CS and CC and also CE. So the cut-off frequency due to the CS can be calculated using the equation FLS. FLS is the cut-off frequency due to this CS. We know the general equation F is always 1 over 2 pi RC. But now, the value of R is not simply R because we have R1 and R2 here. And also RS. Okay. So therefore, the effect of the total resistance in the input side is simply the value of RS plus RI, where RI is actually the parallel of R1 and this R2. Okay, but from the small circuit representation, from this small circuit, we have beta RE here. So therefore, R1 parallel R2 parallel with beta RE gives you the value of Ri. So you have Ri is R1 parallel R2 parallel with the beta Ri. Yeah. Okay. For the effect of coupling capacitor CC at the output side, similar pattern, you have FL due to capacitor CC is 1 over 2 pi R, but the R is influenced by the RO and RL. RL connected to the CC at the output side plus the RO, where RO is actually the RC parallel with the internal RO of this BJT. So if you go back to small circuit representation, this one, you have RO, RC, RL. So therefore, your effect of FLC is simply RO, where RO is RC parallel with internal BJT value of RO plus the RL. So this RL plus the RO. But you have to remember, there is a condition. If RO is more than 10 times of the RC, when two parallel resistors, one is higher more than 10 times, only the other one that is affected. So you have to recall when you have one, for example, 1 kilo ohms parallel with 100 ohms. So what is the effect? Is the small resistor in effect or the higher resistor in effect? So you have to always bear in mind. But if the value is almost the same, less than 10 times, if for example one is 10K, another one is 20, not 20 lah, 15 or 20, less than 10 times difference lah, then you have to evaluate the parallel effect. So this is the capacitance, effect of coupling capacitance into the cut-off frequency FLC. Then we need to calculate the effect of the bypass capacitor CE. So we call it FLE, cut frequency due to FLE. And we use L because we are evaluating frequency response, low frequency response due to this CE. And again, equation is always 1 over, the general format is always 1 over 2 pi R C. And R that we are interested is RE. But RE is due to the presence of the RE that is connected to the emitter here, which is parallel to the R prime S divided with the beta plus the RE of this transistor. And R prime S is simply RS parallel with R1 parallel with R2. Okay, and this one is the ratio of this R prime S divided with the beta value. Beta value is the transistor characteristic. So for a circuit with many coupling capacitor and bypass capacitor, each individual capacitor will influence the cut-off frequency. So let's do one example where we can calculate for voltage dividers arrangement of a BJT. Determine the lower cut-off frequency of this circuit. Given that CS is equal to 10 microfarad, CE is 20 microfarad, CC is 1 microfarad, and then individual resistance, RS, this one is 1K, R1 40K, R2 10K, RE is 2K, RC is 4K. So here you see the value is not very close. And RL is 2.2K. So they are not that much different. But your beta value given is 100. RO is infinity. And VCC supply here is 20 volts. So when you obtain FLC, FLS, FLE, you will obtain different value and you will get different values. And for example, FLS is 6.86, FLC is 25.68, and FLE will be 327. So the highest one is actually the working cut-off frequency for the circuit. Although you have 3 cut-off frequencies, you take only the highest one for the high frequency performance. So how do we get this FLS equals to 6.4. Let me show you. Um, let me okay, we stop there, and I will show you this calculation. In order to determine the FL S first, so you have to calculate beta RE, where you have beta RE is actually 100 kilo ohms, because beta given is 100 for the example, and RE is 2K, so 2 times 100 is 200K, and compared to RE, it is more than 10 times the value of R2. So you can simply take the beta RE value is the value of the beta, okay, which is 100K. And VB is, let's show you if you record. Very difficult. Look at this formula. To find the FLS, and VB here at this point is R2 times VCC divided with R2 plus R1. So you will get VB is actually 4 volts, and you can calculate for IE. From IE, you can calculate RE. So from there, you can obtain the beta RE value. And this beta RE is to calculate for the value of the AV, which is negative 90. And the input impedance will be 1.32. So you get your VI 1.32. So from there, you will obtain and CS. The effect of CS is to calculate for the FLS, which is 1 over 2 pi RS plus RI. You will obtain 1 over these values, 2 pi 1K plus 1.32 times CS given 10 microfarad. So you will obtain FLS is 6.86 Hertz. Then to calculate for the FL, the next one, FLC, you will have this one. To obtain the FLC using this formula, and you will obtain FLC is equal to 1 over 2 pi RC plus RL times CC. Okay, we obtain RC, you use RC only because of the fact that RO is RC parallel with RO, whereas your RO given, what is the value of RO? Is infinity. So RO, small RO is infinity. So compared to that one, infinity parallel with the small one, always the small one is in effect. Infinity, you would assume 1 million. So if you parallel 1 million with 100 kan, given RC, the value of 4 kilo. So therefore, 4 kilo parallel with 1 million, you will get only 4 kilo ohms in effect. So therefore, your FLC is simply 1 over 6.28 times 6.28 is 2 times 3.142 lah. And plus 2.2 because of the RL given. And times 1 microfarad, which is the CC. So from here, you will obtain FLC equals to 25.68. Yeah, 25.68. Okay, to find the last cutoff FLE, okay, to find the FLE, bear with me with my computer that is
Doctor,
yes.
it seems like your laptop is running out of battery.
No, I have lots. 45 minutes, 49 minutes. I have a standby charger, don't worry. All right. Okay, for FLE, when we want to calculate, we have to consider this equation where FLE is similar to the general format 1 over 2 pi RC, but the R must be RE, and RE is actually R capital E, R of this RE connected to the emitter parallel with the internal effect of this BJT plus the RE. And we use that values. So we plug in the values and you will obtain 1 over 2 pi RE CE. The one that you have to calculate is the RE here. And this RE is actually 24.35. And from there, if you plug in, put in your calculator, you will find FLE is 327 Hertz. So now you have 3 from the 3 values of cutoff. The highest one will be the actual working cutoff frequency. So a tedious work, isn't it? But if you use simulation, from simulation, you will not see the other 2. But from calculation, you can see all 3. Okay. Now we move on. I better switch to this one. Okay. role of gain in the body plot. So the body plot not only indicates the cut-off frequencies of the various capacitors, it also indicates the amount of attenuation. Attenuation means the loss of gain. Attenuate, reduced. Okay, the rate of attenuation is sometimes referred as the roll-off. So you will come across what is the roll of gain of the amplifier, for example. So the roll-off means it is not at the optimum level when the gain is attenuated. The roll-off is also measured in dB units. Sometimes it is measured in dB per decade, or sometimes you will also see dB per octave. Okay, octave means a different representation lah, but decade a log base of 10. Okay, dB per decade refers to the attenuation for every 10-fold change in frequency. Okay, because we are using 10 to the power of something, 10 to the power of 1, 10 to the power of 2, 10, always a scale base of 10. For attenuations at the low frequency end, it refers to the loss in gain from the lower cut-off frequency to a frequency that is 1/10 of the cut-off value. So FLS equals to 9 kHz gain is 0 dB. FLS 1/10, FLS over 10 means 1/10 is equals to 0.5 kHz, and the gain is negative 20 dB, and this 20 dB per decade. So therefore we can say the roll off is negative 20 dB per decade. Okay, and dB per octave refers to the attenuation for every two-fold change. To two-fold kuasa 2. Kalau 10, 10 kuasa something. Okay, 10 to the power of something. That is decade. For octave, 2 to the power of something. So for attenuation at the low frequency end, it refers to the loss in gain from the cut-off frequency to a frequency 1/2 of the cut-off frequency. This is a little difficult to see on the graph because the horizontal scale is in the logarithmic scale. So here you will have equivalent of the decade unit in terms of octave unit. So for example, if FLS is 9 kHz, gain is 0 dB. FLS, half of it is equals to 4.5 kHz gain, and it is equivalent to negative 6 dB. So we call it negative 6 dB per octave. So in other words, when it is half, it is 6 dB, but unit is octave. So for 20 dB per decade, is for roll off of consideration of tenfold, whereas per octave consideration of fold, twice or half, ratio of power of 2 lah. Okay, all those are referring to the response of low frequency for BJT transistor. Now for FET transistors, a little bit slightly different. The FET amplifier, we have coupling capacitor also, but because of FET, we have gate drain source. For BJT, you have base emitter collector, but for the FET, gate drain source, the terminals of the transistors. So now your coupling capacitor, you label according to the type of transistors. So when you have FET, the capacitor connected to the gate is called CG. The capacitor that is connected to the drain is called CD. But we also can call it as CC juga lah. And source here, the source of this FET, we have CS here. Don't confuse. CS is not C at the source input, but rather CS is actually at the source of the terminal source of the FET. So therefore, you will have coupling capacitor, CG, CC, and the bypass capacitor CS. Okay. The coupling capacitor CG, the effect of coupling capacitor, similarly, you will have FLC. Each of these three capacitors, two coupling capacitors, CG and CC, and one bypass capacitor CS, will introduce effect on the cutoff frequency. So you can calculate FLC equals to 1 over 2 pi times a total resistance R signal R6 here plus Ri, because it will appear a series of resistance to the gate of this FET, where your Ri is actually Rg. Okay, this Rg is introducing the Ri for this FET. So for the CC effect, which is the coupling capacitor at the output, the cutoff frequency due to the CC can be calculated as FLC, which is equivalent to 1 over 2 pi. The total resistor at the CC is RO plus RL times the CC lah, where RO is actually the RD, R connected to this drain, parallel with the internal RD of this FET. And lastly, you need to calculate also the frequency cutoff due to this bypass capacitor CS. So you will have equation of FLS is equals to 1 over 2 pi R, and this R is going to be R equivalent times the CS, where R equivalent is the RS here, parallel with this internal resistance from the field effect transistor, which is 1 over GM, at which RD is infinity value. And GM is normally given. Okay. Similarly, once you get the value of cutoff frequency due to CG, CC, CS, then you plot it and take the highest bit, the highest frequency as the actual cutoff frequency for the circuit. Okay, the capacitor that has the highest lower cutoff frequency is the closest to the actual cutoff frequency of the amplifier. Okay. Next to the coupling capacitor, you will have Miller capacitance. A Miller capacitor is actually the hidden capacitance within the FET. And this Miller capacitance is due to the presence of PN junction. Any PN junction can develop the capacitance. This capacitance becomes noticeable across the BJT base collector junction in a common emitter amplifier operating at high frequencies. Okay, and it also become noticeable for the FET gate drain junction in a common source amplifier at high frequencies. So if you consider here, these Miller capacitors are obvious for high frequency performance only. And these capacitance are represented as separate input and output capacitance, which are called the Miller capacitance. And this Miller capacitance we refer as CMI is actually 1 minus the gain AV times the CF, because if you represent the circuit as a black box having a gain of VO over VI, the capacitance you have CF here, and you can note that the amount of the Miller capacitance is dependent on the inter-electrode capacitance from the input to the output. And also it depends on the gain. So therefore, your CMI is actually 1 minus AV. 1 minus AV ni is actually the feedback value. Okay. And the output, Miller output capacitance, if the gain AV is considerably greater than 1, then the Miller output, CMO, is almost the value of the CF here. This one is Miller input, okay, which is 1 minus AV, but for the Miller output is taking the value of CF only. So high frequency analysis, compared to the low frequency, when you evaluate high frequency, you will produce a low pass filter. But when you evaluate the low frequency, you get the high pass filter response. So dia terbalik ya. And we can derive similar to the low frequency response. But now you measure the output across the capacitor. So consider this as a passive filter comprising of a resistor and capacitor. When you measure output across the capacitor, you will get the response of a low pass filter. But if you have RC circuit, you measure output at the resistor, you will obtain a high frequency response, high pass filter lah performance. When the frequency increase, the capacitive reactance will decrease, resulting kind of short circuit, producing less voltage output, and the gain will decrease. Okay, and the gain is simply a value of 1 over 1 plus J F over F2. And now we refer to F2 because it's in the higher region. Magnitude and phase, AV is equals to 1 over set of 1 multiply 1 plus F over F2 square of them. And tangent inverse of F over F2 will be the phase angle, phase response. Okay. So similarly, you will have F2 will be measured at a drop of 3 dB or 70.7%, or in the octave unit, it should be at -6 dB per octave. This one, -3 dB per decade. With increasing frequency, the magnitude drops off at 6 dB per octave or at 3 dB per decade. Okay. For BJT amplifier high frequency response, the Miller capacitance we call wiring capacitance, junction capacitance, parasitic capacitance, wiring capacitance, coupling capacitance, bypass capacitance. So many kinds of capacitor will be present when you are using BJT transistor. So this coupling capacitor CS, CC, CE are the physical capacitor that you attach to the circuitry. Despite of having those physical capacitors, when you use a BJT transistor, you will have internal resistance wiring due to the presence of the PN junction. You will have between base and emitter, base and collector, you have CBC. Between the base and the emitter, you have CBE. Between the collector and emitter, you will have CCE. And here you have CWI wiring and 4 internal capacitance that is not seen. But CW wiring ni, you have 2. One is CWI at the input side and you have CWO at the output. So those with dotted lines are actually hidden capacitance with the transistors, within the transistors circuit itself. So altogether ada berapa tu? Sini ada 5 internal capacitance plus 3 external capacitor coupling and the bypass. So you hold together, you have 8 capacitor to consider. 1, 2, 3, 4, 5, 6, 7, 8. So it will be difficult to handle when you have so many capacitors. So if you have multi-stage frequency effect, such as you combine low pass and bypass, you will have a band pass filter. And each stage has its own frequency response, but the output of each stage is affected by capacitance in the subsequent stage. For example, the output capacitance CO is affected by the input Miller capacitance of the next stage, and so on. So the more stages you have, the more effect, because each stage has its internal capacitance influence. So for example, if you have here N1, N2, N3, when you have many cut-off frequencies, the actual cut-off, you just take the middle one, the innermost one. The outer is not visible because the innermost will be taken over, outperform the outer layer. Okay. For similar to the low frequency response analysis, if we evaluate at high frequency analysis, the equivalent RE model, you can separate into hybrid circuit where you can separate input from the output, and here you will see wiring capacitance, CBE, CMI. At the input side, total CI is CWI plus CBE plus CMI. At the output side, you will have CO is equals to CWO wiring effect plus CCE plus CMO. And CI will be at this side, CO will be at this side. At high frequencies, capacitors CS, CC, and CE are assumed to be short circuit because high frequency short circuit lah. So therefore, CI is then take the effect of the wiring capacitance, CBE plus CMI. CO take the effect of CWO plus CCE plus CMO. So the actual value of CS, CC and CE are not going to taken into consideration because we are considering high frequency now. And when you have this circuit, if we evaluate the Thevenin for the input side, you are going to have R Thevenin is equals to RS parallel with R1, parallel with R2, parallel with RI. And there is one CI here. And the CI comes from the total of CWI plus CBE plus CMI. Okay, for at the output side, we have RTHO equals to RC parallel RL parallel RO. And this is CO, which takes the value of CWO plus CCE plus CMO. And from the Thevenin circuit, at very high frequency, the effect of CI is to reduce the total impedance. Therefore, voltage across CI is reduced and the current IB is also reduced and the gain of the system will drop. So you have at high frequency less no gain, attenuated. For input high frequency FHI, we will have again if we consider voltage divider configuration for this BJT, you will have RTHI is RS parallel R1 parallel R2 parallel with RI, where your RI I think it's R1 R2 RI, and CI is this CWI plus CBE plus CMI, where CMI is 1 minus AV times CBC. CBC is this value. For the output, high frequency cutoff FHO is 1 over 2 pi RTHO times CO. And RTHO is equivalent to RC parallel with RL parallel with the internal RO of the BJT. And the CO is from the wiring CWO plus CE plus CMO. Okay. HFE or beta value variation, the effect of the variation of beta for the BJT. So if you have the HFE parameter or the value of the beta of a transistor varies with frequencies. So F beta is actually equivalent to the value of 1 over 2 pi times beta mid value RE times CBE plus CBC. And if you are using HFE here, HFE is 0.707, but for HFE equals to 1, this is the value, and the slope here is negative 6 dB per octave. Okay, an example, okay, example 2, you are given a BJT circuit. You are to sketch the frequency response for the low and high frequency region. Given that RS, R1, R2, RE is 2 kilo, RC is 4 kilo, RL is 2.2. Similar value to the previous example. Beta is 100, RO infinity, and BCC is 20. I think the same example. The previous example, low frequency response, we do not evaluate the Miller effect. And here in this problem, we are given the internal CBC, CVE, CCC with a very small value capacitance, picofarad. External capacitor normally have the unit of micro, but the internal is having 1000 times smaller than the physical. So here you have all pico values. 36 pico, 4 pico, 1 pico. And the wiring also in unit of pico. CWI is 6 pico, CWO is 8 pico. You can do the same and you can calculate this one, if I'm mistaken. 52, yeah. Slide number 52. This one. I want to show you the example. What is that here? The effect of high frequency response on I should change. High frequency response BJT, where we have this is the one where you can calculate example here you are given the value of this circuit. That is okay. I put side by side. Here you will see given RS 1 kilo ohms, 40, 10 to 4K 2.2 and so on, with the CS and So you're given the value of 6 picofarad, 8 picofarad. We want to find FHI and FHO. But FHI ni, due to the CS, due to the CW and so on lah. So many values. So you have to calculate. And to determine the FH, um, due to influences from the many capacitance present, you can oh, it's not showing my okay. You find Ri is given as 1.32. We given one the Ri value. Okay, this one is actually taken from the previous example, example 1. Ri and the AV mid for the amplifier is negative 90. So what we want to calculate is Ci. Ci is Cwi plus Cbe plus 1 minus AV. So 1 minus 90, 1 minus minus is 1 plus 91. And you will get Ci equals to 406 picofarad. FHI is 1 over 2 pi RTHI and times Ci. So you will get FHI is 738.24. Okay, for RTH2, kenapa dia hilang? CO, you will get CWO plus CCE plus CMO. Then you will obtain 8.6 megahertz. Okay. To find the cutoff FB, you will obtain. Check. You will obtain for this one. FHO is 8.6. But actually, if you look at this example, you will have many values to calculate. Yeah. So here, you will have 738 kilo and 8.6 mega. So that would be the difference between this one. I go back to this one. Okay, the last part I want to show is on the FET amplifier, Miller effect, because we are evaluating high frequency, and we have internal capacitance CGD, CGS, and CDS. Similar to the BJT, we also have wiring capacitance, CWI, at the input, and wiring capacitor at the output, CWO. So again, we have 8 internal, not inter 5 internal plus 3 external or physical capacitance for the circuit. So the input frequency, similarly, FHI is equals to 1 over 2 pi RTHI, CI, CI, CWI plus CGS plus CMI, and CMI is 1 minus the gain times CGD. CGD will be this one at the input side, CMI. And RTHI is R6 parallel with RG. Okay, the output side for FHO is equals to 1 over 2 pi RTHO CO, and CO is equals to CWO plus CDS plus CMO, and CMO is 1 over 1 over AV, and RTHO is equals to RD parallel with RL parallel with the internal FET resistance, R small d. So for multi-stage amplifier, similarly, once the cutoff frequencies have been determined for each stage, to account the shared capacitance, they can be plotted. Take only the highest lower cutoff frequency and the lowest upper cutoff frequency, which gives the closest response to the actual response of the amplifier. So you just take the internal envelope. That will give the actual performance. The external part will be not obvious, and the main influence come from the internal envelope here. Okay. Okay. I think that's all for today, and the last 2 slides is about square wave testing. I will cover that later on. By the way, tomorrow we will have no online class. I will just upload some videos for you all to test. And Tan Chong Yong is requesting control here.
No, mispressed. Sorry,
Just
madam.
okay. So tomorrow, because I have online conference, and at the same time, I also have moderation meeting for program, master program. So everything overlap at the same time. So I will post some lecture videos for you all to learn on your own. So we will meet again next week, and I will also post some exercise. I haven't post from this slide. I don't. Oh, for my lecture, yes, I have. But for the material that I upload in UKM Folio, I didn't assign any questions yet. But you can use the book. These are the selected questions that I planned. Similar to Dr. Fazila, I will give exercises in which students have to do, and those exercises will be exercise for you all to develop understanding of the topics that we discuss. It will not be counted for the final grade because the final grade will be based on a project on the OPAM circuit later on, and one test from my chapters, the chapters that I will be covering with you all. So altogether we have 3 e-tests lah. Dr. Fazila 1 e-test, myself 1 e-test, Dr. Siti Salasia 1 e-test, and the other assessment will be a quiz from Dr. Fazila, project from me, and I think assignment from Dr. Siti. So altogether there are 6 assessment only. So there is no final exam for this course. So you are lucky. Hopefully you can do well, and we understand the difficulties of learning online. Not just students facing big challenge. The lecturers are also learning a lot of new things, and we are also struggling. So until then, I see you all next week then. So thank you for your attention. So bye-bye. Thank you.
Thank you, Doctor.
Thank you, Doctor.
Thank you, Doctor.
Thank you, Dokter.
Thank you, Doctor.
Saya
Lalu
Bodoh.
Nandli.
How to